Today, we're really getting into the heavy metal. We've got some documentation here about the real workhorses on those massive LNG carriers.
Yeah, the high-duty centrifugal compressors. These things are, well, they're the heart of the gas management system.
And high duty, or HD. I saw it also called VR, vapor return.
That's right. Same machine, different labels, HD, VR. You'll hear both. But yeah, high duty is probably the more common term you'll find in the manual's mission critical kit.
Absolutely. Fixed speed machines moving just enormous amounts of volatile gas.
Huge amounts.
So our goal today, our mission, if you like, is to cut through some of the dense engineering speak.
Yeah, get past the diagrams for a bit.
Exactly. We're not just looking at the big shiny spinning bits, but all the, the layers of support and safety stuff that keeps these things actually running.
And stops them from, well, blowing up. The stakes are high.
Definitely high. I mean, the specs alone, what was it, up to 35,000 cubic meters an hour flow rate?
Staggering volume. And the speeds. That shaft is spinning between like 11,200 and 11,400 RPM.
Wow.
Yeah. There's just no room for error at those speeds. None.
Okay, so let's get into this sort of dual life these compressors have. It makes the engineering fascinating, but also pretty demanding.
It really does.
What are the main jobs? We know it handles the boil-off gas, the BOG.
Yep, standard stuff. Natural vaporizing of the cargo.
And returning vapor to shore when loading.
Okay. That's job one, the everyday task, if you like. But the really tricky part, the thing that makes this machine special, is the thermal range it has to cope with.
Right, the temperature swings.
Exactly. So normal operation, you've got LNG vapor coming in super cold. We're talking minus 140 degrees C sometimes.
Minus 140 C, just brutal cold.
It is. But then, picture this. The ship needs to go into dry dock. Tanks need to be warmed up, made gas-free.
Okay.
The same machine has to switch gears completely. It circulates hot cargo vapor, sometimes up to 80 degrees Celsius. Hot.
80 C from minus 140.
Yep. And it keeps doing that until the tank's secondary barrier, that safety layer, gets up to at least plus 5 degrees C.
So hang on. One machine, a 220 degrees Celsius operational temperature window.
Pretty much.
That requires incredible engineering tolerances. And it just screams high risk, doesn't it?
It absolutely does. Which is why safety starts with, well, physical separation, keeping things apart.
Also,
the motors driving these compressors, they're huge. We're talking 6.6 kilovolt electric motors, over a megawatt each. Big power.
Right.
They live in a completely separate room, an electric motor room protected by a solid steel, gas-tight bulkhead. Segregation.
Makes sense. Keep the potential sparks well away from the flammable gas. Basic safety.
The most basic principle, yeah.
But power has to get through somehow, right? You still need a drive shaft punching through that bulkhead.
You do, and that's the critical point.
That penetration point. Feels like the Achilles heel.
It is, potentially. It goes through a mechanical seal assembly, and the integrity of that entire gas-tight bulkhead relies completely on that seal.
And what keeps the seal working?
Pressurized oil. A continuous barrier of oil, basically. If that oil pressure fails...
Gas meets motor room. Bad news.
Very bad news. High-speed components, potentially high voltage?
Yeah.
Nah, good.
Okay, so that oil barrier, let's dive into that. The lube oil system, the LO system, you called it the lifeblood earlier.
It really is. It lubricates the gearbox, the high-speed bearings, vital stuff. But crucially, it also provides that pressure for the bulkhead seal.
So redundancy must be key here.
Oh, absolutely non-negotiable. You've got a big sump, like 400 liters of oil, and two pumps, okay. Main and backup. Exactly. But here's the clever bit, or maybe the slightly scary bit, depending on how you look at it. The main operational pump, it's mechanically driven, off the gearbox itself.
Wait, mechanically driven. So if the main motor trips and the shaft starts slowing down...
You lose your main oil flow almost immediately as the speed drops.
Whoa. Okay, so that makes the auxiliary pump absolutely critical, like life or death critical.
Precisely. The standby pump is electrically driven, and the control logic is instant. Main pump fails, or even if the LO supply pressure just dips below the alarm set point, say 220 kPa.
Which is about, what, 32 psi?
Roughly, yeah. If it hits that, boom. The auxiliary electric pump kicks in automatically, no questions asked. Keeps that pressure up.
And keeping it warm seems just as important. I saw notes about a steam heater in the sump, and long heating times. Like up to 6 hours.
Yeah, that's crucial too, especially in cold climates. It's not just about warming the oil itself, that 400 liters.
Ah, right. You're warming the whole assembly.
Exactly. Tons of cold steel, the gearbox casing, the bearings, the shaft, It all needs to come up to temperature slowly and evenly.
To avoid condensation.
That's the main enemy, water in that high-speed oil system. Fatal for bearings. So you gently warm it all up, maybe 45 minutes if it's warm, maybe 6 hours if it's freezing, to get the oil into that sweet spot, maybe 38 to 47 degrees C.
Okay, makes sense. Now, safety nets, the pressure trips. You mentioned the 220 kPa alarm.
Yeah.
That's the warning shot. What happens if it keeps dropping?
Then you hit the hard stop, the low pressure trip. If that LO supply pressure tanks down to maybe 80 kPa gauge, or sometimes it's set around 103 kPa.
Huh.
Or if a bearing temperature suddenly spikes, hits the high alarm, say 75 degrees C.
Then what?
Immediate shutdown, hardwired trip. The system doesn't ask permission. It just slams the brakes on, saves the machine. That's the priority. Asset protection over operation.
Wow. And even just routine filter maintenance is tied in.
Yep. Duprex filters, constantly monitored. If the pressure difference across the active filter gets too high, shows it's clogging, maybe 80 kPa difference or so. Yeah. That triggers an alarm, maybe even a trip if ignored. You have to switch over to the clean filter immediately. Can't risk starving the system.
Okay, so lubrication is one massive pillar, but you said there's another guardian system, an invisible firewall.
That's the seal gas system using nitrogen, and it does two absolutely vital jobs.
Okay, what are they?
Job 1, stop any lube oil mist from getting sucked from the gearbox into the process gas stream. You need to keep that LNG vapor pure.
All right, contamination control.
Job 2, and this is maybe even more critical for the machine's survival, stop that ultra-cold minus 140°C process gas from leaking back into the gearbox area.
Because that would cause
instant thermal shock, freezing the oil, shattering components, catastrophic failure, basically.
So how does the nitrogen create this barrier? Where does it go?
They inject dry nitrogen. They make it on board the ship into a space strategically located between the gear shaft bearing on the oil side and the main compressor wheel on the process gas side.
Creating a buffer zone.
Exactly, a nitrogen buffer. But here's the really smart part. The pressure of that nitrogen isn't just constant.
No. How does it work then?
It's dynamic. The control system regulates the nitrogen pressure based on the compressor outlet pressure.
Okay, why tie it to the outlet pressure? Why not just set it high and forget it?
Because the process pressure inside the compressor changes with the load, right?
Sure.
So by tying the nitrogen pressure to the outlet pressure, making it always just a little bit higher than the process pressure.
You guarantee the nitrogen always wants to flow outwards.
Precisely. It ensures a positive pressure gradient away from the nitrogen buffer zone, both towards the cold process gas side and towards the oily gearbox side.
So it's constantly pushing back against both potential leaks. Clever.
It really is. It means the barrier holds firm no matter what the compressor's doing. It prevents the cold gas ingress and stops oil mist escape. True dynamic seal.
And what happens to the nitrogen that does leak out, say, into the gearbox?
Good question. It gets mixed with the oil vapor in the sump, then it's separated out using a mist eliminator and safely vented to the atmosphere. Keeps the system clean and safe.
Okay, we've covered protection. How about control? These things spin at a fixed speed, 11,000 RPM plus, right?
Yep, constant speed.
So how do you actually control the amount of gas flowing through? You can't just slow the motor down.
No, you can't. That's where the inlet guide vanes come in. IGVs.
IGVs.
Okay, what are they? Think of them like adjustable blades right at the suction inlet of the compressor. They're moved by pneumatic actuators.
And they control flow how? By opening and closing like a valve.
Not quite like a simple valve. They rotate. They change the angle at which the gas enters the compressor impeller. They can swing from about minus 30 degrees to plus 80 degrees.
So by changing the entry angle, you influence how efficiently the impeller grabs the gas.
Exactly. You're essentially pre-swirling the gas, which modulates the flow and, crucially, helps maintain the target pressure in the ship's main vapor header pipe.
Got it. But controlling flow, there's always a danger zone, isn't there?
Yeah.
Pushing the flow too low. Compressors surge.
Surge, yes. That's the big enemy for any centrifugal compressor. It's basically flow instability.
What happens?
If you try to operate below the minimum stable flow point for that machine, the gas flow through the compressor actually breaks down. It can momentarily reverse direction inside the machine.
Reverse? That sounds violent.
It is extremely violent. You get rapid, huge pressure pulsations, massive vibration through the shaft. It can physically destroy the compressor internals in minutes if it continues.
Okay, so how do you stop that? There must be an anti-surge system.
Absolutely. Standard practice. It uses a recycle valve, sometimes called a hot bypass valve, or HBV.
Right. Connecting discharge back to suction.
Exactly. The control system constantly monitors where the compressor is operating relative to its known surge limit line. If the operating point gets too close, the recycle valve automatically starts to open. It bleeds some of the high-pressure discharge gas back into the low-pressure suction side,
Giving the compressor more gas to breathe, even if the ship doesn't need it.
Precisely. It guarantees there's always enough flow going through the compressor itself to keep it stable and away from that surge point, regardless of the actual downstream demand.
Now, the documentation really emphasized the detection method.
Yeah.
It wasn't just looking at low flow. It was looking at the pressure slope.
Yes, that's a more sophisticated approach because surge isn't just low flow, it's that rapid instability.
So what's the signature it looks for?
It looks for that characteristic pattern in the discharge pressure. A sudden, sharp drop, immediately followed by a sharp rise as the flow momentarily recovers, then another sharp drop. That DPDT pattern, the rate of change,
is a much faster, more reliable indicator of actual surge happening than just watching the average flow slowly decrease.
Exactly. It catches the instability itself much quicker.
And the ultimate protection, if surge keeps happening.
The system counts. If it detects that surge pattern repeatedly, the spec usually mentions something like 6 times within a short window, maybe 2 minutes.
6 surges in 2 minutes.
Yeah. If that happens, the system basically decides, okay, something is fundamentally wrong with the process conditions. We can't operate safely like this.
And it shuts down.
Full compressor trip, immediate shutdown, no messing about, protect the asset.
Wow. Ruthless logic. Okay, let's shift to actually getting one of these things running. The startup sequence sounds intense.
It is. Very procedural. You can't just walk up and hit start. There's a whole pre-start checklist mandated.
Yeah. We mentioned the lube oil heating already. Potentially 6 hours.
Yep. Got to check that LO sump level is correct. Got to run that auxiliary LO pump for maybe 30 minutes first.
Pre-lubrication.
Exactly. Ensure all the bearings have fresh oil before that shaft even thinks about turning. You need cooling water available, instrument air pressure up.
And the IGVs? Where do they need to be?
Critical point. They must be confirmed fully closed or at their minimum position, 0% or maybe less than 5% open, depending on the specific setup.
Why closed? To minimize the starting load.
Precisely. You want the absolute minimum resistance against that massive electric motor when it first tries to spin up that heavy rotor assembly. Reduce that initial current surge.
Okay, all checks done. Green lights across the board. Operator hits start. What happens next? I saw something about a really tight timer.
Yeah, the sequence timer. This is pure electrical protection. When that start command goes out, the control system absolutely must receive a confirmation signal, drive motor running feedback within about 3 seconds.
3 seconds. That's it for that huge motor.
That's it. It sounds incredibly short, I know.
Why so strict? What's the risk?
Massive electrical overload. That motor draws enormous current when starting inrush current. If it's energized, but for some reason fails to get the rotor accelerating properly, maybe a mechanical jam, maybe an electrical fault.
It just keeps drawing that huge current.
Exactly. And that sustained overload would cook the motor windings, potentially damage the switchgear, cause havoc on the ship's electrical system, so no running signal back within 3 seconds. Instant trip. Protects the whole electrical infrastructure.
Okay. Assuming it starts, runs fine, then comes shutdown. Power's cut, but that rotor's still spinning down from 11,000 RPM. Lots of inertia.
A huge amount of stored energy. And residual heat in the bearings and gearbox. The danger isn't over just because the motor is off.
So coast down protection.
Absolutely vital. When the unit is stopped, whether it's a normal stop or an emergency trip, that auxiliary electric lube oil pump is commanded to start, or if it was already running, it stays running.
And it stays running for hours.
For the entire coast down period, it's locked in auto mode. This could be 20 minutes, 30 minutes, sometimes even up to 60 minutes after certain types of local emergency stop.
All that time just circulating oil through a machine that's stopped.
Well, stopping. It needs that continuous flow of cool, pressurized oil to carry away the residual heat from the bearings as they slow down and to keep them properly lubricated right until they are stationary. Skipping that guarantees bearing damage.
This whole system, it's just layer upon layer of protection, isn't it? Yep. Dynamic, adaptive, redundant.
It has to be. Everything we've talked about, the LO system, the seal gas, the surge control, the startup checks, the coast down lube, it's all built around that core idea. If in doubt, shut down. Sacrifice the operation to save the multi-million-dollar machine.
Every pressure reading, every temperature, every vibration signal. It's like a constant negotiation between running and tripping.
Pretty much, yeah. Real-time risk assessment, constantly happening.
Which brings us to one final, really provocative detail I found in the manuals.
Ah.
A hard rule about emergency stops.
The ESD trick count.
Exactly. It says quite clearly, if the compressor is tripped using the main emergency stop device, the ESD button, 8 times, just 8 times during its entire operational life.
Then you have a problem.
Well, you have a mandate, a mandatory physical inspection. Open it up, check the internal gears, check the bearings.
8 trips. That's it. And you're talking a major overhaul, essentially. Huge cost, huge downtime, all built into the operating procedures.
It is. So here's the thought we want to leave you with today. Why? Why demand such an expensive, invasive inspection after only 8 successful emergency shutdowns? These weren't failures. The system worked. It stopped safely.
Good question.
What does that tell us about the kind of the unseen stress, the cumulative impact, the sheer violence that even a controlled emergency stop imposes on components, spinning at over 11,000 RPM? Yeah. Even when it works, maybe it's still doing some hidden damage.
Something to think about, definitely. That razor-thin margin. Maybe it takes its toll, even when things go right.
Think about that next time you imagine these massive machines keeping the gas flowing.